Okay, so now we're looking at lead 2 iodate. So we have PbIO3 with a 2. So our KSP is going to be lead positive 2, and then iodate with an exponent 2. Okay, so now remember when we're doing our X values, let's just quickly do this here. So our KSP, we can get this from our data table. So we have 3.7 times 10 to the negative 13. So our PB, our lead, is going to be X, but remember the iodate is going to be 2X. So really this is going to be X and then 2X squared. So remember that the square will impact both the 2 and the X. I know it's kind of like simplistic to say, but I mean, you never know, you need a reminder. So this is like X and then 4X squared. So then when you have this other X, this becomes 4X to the 3. Okay, so something to just remember when you're factoring that out. So if this was 3X to the 3, right, that would be 3 times 3 to the exponent 3 was that 27, and then X to the 3. So just be mindful when you are doing that to apply the exponent to both the number and the variable. So now we're just going to isolate for X. So we'll divide by 4 on both sides. And then, of course, we would have to take the cube root to get X on its own. So we end up getting 4.52 times 10 to the negative 5 moles per liter being equal to our X, which is essentially our solubility. Okay, and then we have another one that's in grams per liter. So we would have to do our moles per liter first, like normal, and then we would have to convert to grams per liter. So strontium fluoride, when we do our KSP, is going to be strontium, and then we have fluorine squared. So KSP, the value from our table, is 4.3 times 10 to the negative 9. This is going to be X, and again we have another 2X squared, which is going to be 4X to the 3. So once we isolate for X, right, by factoring that out, you should get 1.024 times 10 to the negative 3 moles per liter. And then, of course, we need to convert this into grams. So we would have our molar mass for strontium fluoride is 125.62 grams. So we get 0.129 grams per liter. Okay, so number 2 says, what is the concentration of hydroxide in a saturated solution of iron 3 hydroxide? Okay, so let's take a look. We have iron 3 hydroxide. Let's write the dissociation expression, or equilibrium here. Okay, so we want to know what the concentration is. So here is our expression. So this is essentially going to be X and 3X, right? So if we have a KSP, we're going to have Fe positive 3, and then we're going to have hydroxide to the exponent 3. So this is actually exactly what we were mentioning before. So KSP we would look up on the keep saying solubility table, but the KSP table. So this is one of the examples that's very, very, very low solubility, times 10 to the negative 39, my goodness. So our Fe is X, and this is going to be 3X to the 3. So this is going to be, after this is all said and done, 27X to the 3 with another X, 27X to the 4, right? But we would do the same thing, right? We would still want to factor out for X. So we would have to take the quad root, I guess, is that what the cube root, quad root? Anyway, so we would take the square root with the value 4. So there is, if you need me to show you the button when I see you once again, There is a button on your scientific calculator that looks like this, where you can input really anything. So you probably have a square button and even a cube button, but there is one that you can apply multiple different squares, multiple roots to. Okay, so in this case, right, we end up getting a value here once everything is said and done of 9.9 times 10, you can leave a 1, times 10 to the negative 11. So very, very, very low solubility. All right, so number 3, our last example here. So we are going through what mass of calcium oxalate is dissolved in this volume of a saturated solution. So in other words, we have to determine the number of moles per liter first, and then we can determine our number of moles since we know the volume here. So let's start off as our normal, our normal method here. So we have calcium oxalate, and then they're both a charge of 2, so it's going to be a 1-to-1 ratio. So our KSP is going to be really just x squared here. So KSP, when we look that up, is 2.3 times 10 to the negative 9, and then this is going to be x squared. Take the square root. X ends up being 4.796 times 10 to the negative 5 moles per liter. And now that we know that, we can determine this. You could show this in full, or I just kind of mentally just converted this into liters. But you can show this in full, going milliliters, and then the additional step of going into liters. And then we have, we wanted this in grams, right? So we would have in 1 mole, the molar mass of calcium oxalate is 128.097 grams. Ooh, it's kind of squished in there. So that would cancel out our moles. This would leave us with a gram value. So we have here actually we do have sig figs. We have 3 significant figures because of the decimal point at the end of that 650. So this ends up being 3.99 times 10 to the negative 3 grams. Okay, thanks everybody. I know that I won't see you for another, have a great week. I know I'm not going to see you until November or something, November the 8th or something like that. But have a good week. Have a happy Halloween, and we will see you soon. Bye, everybody.